Welcome to the first lecture for Advanced Research Methods 2, which is the basic introduction to correlation and regression analysis. In this, to kind of set the stage for what to expect with these pre-class lectures, these will be, for the most part, theoretical, for lack of a better term. It's not technically theoretical, but there will be no application. So this first online lecture is just to give you a basic idea of what to kind of expect from the class and what, or a way to kind of conceptualize correlation and regression analysis. I hope with this initial lecture that we can put to rest, so to speak, some of the misperceptions about what regression is, and the differences between regression and ANOVA, and get started with a very kind of basic understanding of regression. Some of the things that I'm going to talk about in this brief lecture, and it will be brief, are pieces of regression or aspects of multiple linear regression that will be covered in more detail in future chapters. So you can consider this kind of a bookend as a way to start and think about things that are going to be coming. So by way of an overview, let's talk a little bit about regression. So regression is it is a highly general and therefore very flexible data analytics system. So you can use regression whenever you have some sort of a quantitative variable as a dependent variable. A quantitative variable meaning that it is measured in some way that can be defined based on numeric values. So -5 to +5 and everything in between, 0 and 1, 0, 1, 2, 3. It cannot be used as a way to quantify qualitative data. And so, although sometimes we can use predictors that are qualitative in nature, or at least quasi-qualitative in nature. This is a very kind of broad, sweeping statement, and it's done quite intentionally. So the form of the relationship between x and y, and that's what we're always talking about when it comes to multiple linear regression, is the relationship between x and y, or multiple x's and y. And in the case of multiple dependent variables, sometimes multiple y's as well. We're not going to get into that in this class, but I want you to kind of think about multiple linear regression as a basic algebraic formula. Everybody remembers that we learned y equals ax plus b, or you might have learned it y equals mx plus b or mx plus a or something along those lines. But the general idea is that you have some value y, and it is associated with some other value x, and when you have several x's and several y's within a given data set, you can plot a simple line through there, right? And that's basic linear algebra. And that's what multiple regression is. It's trying to plot a line, a slope, an m, through some sort of cloud of data, as you'll see as we get going here. So the form of the relationship between x and y is not constrained. It can be very simple, or it can be very complex. It can be a simple straight line. It can be a curved line, or a quadratic multiple curved line. It can be general, or what we call main effect, or the line can be conditional on other types of variables that are in your model, in which case we call those conditional effects, or it can be combinations of all of these things. We have the nature of the research factors expressed as independent variables is also not constrained. They can be quantitative or qualitative. You can have main effects or interactions. Analysis of variance is in its most basic form a a type of regression, and we're going to learn how to and take examples on how to do regression or ANOVA in regression. Um, so the nature of the dependent variable is also not constrained, though it does have to be, as I noted earlier, quantitative in some way. Like all statistical analyses, we have basic model assumptions about the data that we are analyzing, um, and we have to be able to um, uh, if not meet those assumptions, note the limitations when we can't meet those assumptions. And in future chapters, we'll talk about ways that we can transform our data in order to bring them to a closer approximation of assumptions when our assumptions are violated. And multiple linear regression is about testing hypotheses. So it is, in a real sense, broadly applicable to hypotheses that are generated by researchers in the behavioral sciences. If you go to your textbook, you will see a whole slew of potential hypotheses that can be tested using multiple linear regression or multiple regression. One thing that I want you to always be thinking about is that linear regression is a tool, right? In fact, all data analytics are a tool. Scientists are only as good as our data analytics, but behavioral scientists, and we'll get to this in a little bit, don't focus, with the exception of quantitative psychologists, don't focus so much on the statistical piece, right? Statistics give us a way to test the hypotheses that we have about nature and or the nature of human behavior. And that's really what regression is. Don't get too wrapped up in the math. The important piece is to get wrapped up in the analysis that you're doing only insofar as it's able to provide you with a sound potential test of whatever hypothesis you're aiming for. Each hypothesis that you have proposes some form of relationship, at least within the context of regression, between one or more factors of interest, our independent variables, and our dependent variable. And as I said, in this class, we will just have one dependent variable. There's usually other variables whose effects need to be considered, and this is one of the reasons that regression is so great, because in the context of regression, we can statistically control for other variables that might affect our outcome. You cannot do this, well, you can sort of do this, I guess, in ANCOVA, but you can't do this in basic ANOVA, right? The idea is that you have strict control of your independent variable. All right, let's talk about prediction models real quick. Multiple regression or correlation allows for a practical prediction of problems where the goal is to forecast some sort of an outcome based on data that were collected earlier. For example, college admissions committees might be interested in predicting college GPA based on high school grades, college entrance exam scores, ratings of students by high school teachers, etc. In the absence of any type of theory, and sometimes we don't have any theory to fall back on, you can use multiple regression in a purely exploratory fashion. This is called hierarchical regression, not to be confused with hierarchical linear regression, which is something altogether different. Or hierarchical linear modeling, I'm sorry. But hierarchical regression allows you to identify kind of a minimum set of variables that yield the best prediction of a criterion, and there are entering and removing of predictors in a stepwise fashion. This is an empirical approach, not a theoretical approach, and we're going to talk about this, I think, in an upcoming chapter. I think it's chapter 5, I can't remember. We will go through and talk a little bit about using hierarchical regression. There's also some things that we have to understand when it comes to what actually is multiple linear regression. So there's been a misperception that multiple linear regression is only suitable for experimental research. This is not true, and we're going to talk about this in just a little bit. I also want to note that some of the persisting differences in data analytic philosophy that are associated with researchers using MRC rather than ANOVA are some of the are associated with kind of differences between when we think of experimental psychology versus clinical psychology versus sociology within the behavioral sciences. And in truth, none of those things matter. While there might be a bias based on discipline, the underlying mathematical models for ANOVA and regression are no different. Or I may say that ANOVA or regression is a more robust approach than ANOVA is because it allows you more flexibility. Not more robust in the analytics, but more flexibility. So one thing that we should note is that there are, within the context of multiple linear regression, we have several independent variables may be expected to influence a single dependent variable, and these independent variables themselves may be related. The independent variables can take different types of forms, and we'll talk about that as we kind of keep moving along here. Let's talk a little bit about the historical background, and I do mean just a little bit about it. Multiple linear regression actually arose out of the biological and behavioral sciences around 1900. Some of the early people included Galton, who studied, heights and later on IQ. I think he studied IQ. Pearson and Ewell's work on educational issues, and a bit later we start seeing ANOVA and ANCOVA. ANOVA and ANCOVA are traditionally thought of as ways to analyze data when we're using some sort of planned experiments. And regression is traditionally thought of as a way to analyze data when we don't have experimental groups or experimental conditions. One of the nice things with regression versus ANOVA and ANCOVA is we don't have to worry about equal cell sizes or equal numbers of people within cells. And of course, there are ways to handle this with ANOVA and ANCOVA as well. But as I said before, multiple linear regression is just a little bit more flexible when it comes to that. In truth, multiple regression and ANOVA and ANCOVA were developed starting around the early 1900s and grew kind of largely independent from each other, despite the fact that they are basically the exact same or very similar mathematics that underlie each of these approaches. So hypothesis testing and effect sizes. Any relationship that we observe, whether between independent variables and some sort of outcome, or between independent variables and a dependent variable in an observational study or an experimental study, can be characterized in terms of the strength of the relationship, or what we call its effect size. One of the most attractive features of multiple linear regression is that there is an automatic provision of effect size known as the regression coefficient, or the proportion of variance that's accounted for and why. The regression coefficient is a magnitude of slope, and the proportion of variance is the amount of variance in y that slope accounts for, or that variable accounts for. We think of these often in terms of r squared, r being the slope or the relationship between x and y, and r squared being exactly what it is, the squared value of r, which we'll talk a little bit more about this, which is indicative of the amount of variance that x and y have in common, or that they overlap. A lot of the stuff that we will do in class, we'll look at this common overlap in terms of Venn diagrams, and I would encourage you to think about those when you're doing your exam as well. All right, let's keep going. So one of the great things about multiple regression versus ANOVA or ANCOVA is it allows you to account for multiple influences. When you think about a basic ANOVA, you have the outcome variable measured on some sort of ratio or interval scale, usually, some sort of continuous variable, um, and the independent variable being a series of conditions or groups that are controlled by the investigator. At times, though, these conditions or groups are something that we want to evaluate, but we can't readily measure. For example, you might want to examine differences in some sort of trait as a function of biological sex, in which case you can't assign people to be one sex versus the other, right? Alternatively, you might want to look at the relationship between some sort of personality trait and gender being more fluid than biological sex. It doesn't lend itself well to ANCOVA. In addition, you might want to know how age, gender, socioeconomic status, and education all influence, let's say, impulsivity. These definitely don't lend themselves well to ANCOVA or ANOVA. However, in regression, they do. And one of the great things about regression is that it allows you to see the independent correlation of any given predictor, the independent correlation between any given predictor and y, removing the variance that is accounted for between all of the other predictors. So you have the ability to look at multiple influences. In addition, there are relationships between all of the different predictors and each other. So X1 and X2 and X3 and X4 and X5 might be correlated. And regression removes the correlated variance between X1, X2, X1, X3, X2, X3, etc., and only looks at or provides you with the partialed variance between X1 and Y that is independent of all other predictors. So it gives you the ability to see what is the unique contribution of all of your different predictors in predicting Y. This is important for a few different reasons, and one of the most important reasons is it allows us to examine causality. We're going to talk a little bit more about that in future classes. Okay, forms of variables. I'm not going to go through these in a lot of detail. Suffice it to say, we have these kind of four basics. These are things that you should have learned in ARM 1, but we have ratio scales. These are equal interval spaced scales with true 0 points. The most common one that we think of with a ratio scale are things like height and weight, because there is a true 0. Next, we have interval scales. Interval scales do not have a true 0, but they are also characterized by equal spacing. Everything that we do in the context of this class will have dependent variables that are either ratio or interval. The typical interval scale often has a 0, but it's not a true 0. For example, temperature in Fahrenheit has a 0, a measure of 0, but that doesn't mean that there is no temperature at 0. It just indicates that 0 does have some sort of meaning in that context outside of none. Then we have ordinal. Ordinal are scales that are not equally spaced. They generally do have a true 0, though. They, not necessarily always, I guess, but they tend to be oftentimes ranked, and the kind of prototype of an ordinal scale are the places that people came in a race or something like that. And then we have nominal scales. Nominal scales are, they can be qualitative scales. They tend to be things like gender, political party, psychiatric diagnoses, etc. They are discrete groups that are not necessarily ranked in any sort of fashion. Okay, shape of relationships. So in this class, we are going to focus primarily on linear relationships. However, in the second half of this class, we do start discussing, actually just before the final, or just before the midterm, we bring up the topic of nonlinear relationships. And this is nonlinear only in the sense of the relationship between x and y, that with the assumption that y is a continuous variable. Now, the fact that y is a continuous variable does not mean that a curvilinear relationship for x will not or does not exist. Oftentimes they do, and at times failing to account for this can result in specification error, which we'll talk about here in a second. In addition to or nonlinear and linear relationships, we have general and conditional relationships. The general relationship is often referred to, in ANOVA, a general relationship is referred to as the main effect. In regression, we're able to look at something called conditional relationships. And so we can look at conditional relationships, which are an interaction between two dependent variables. Sometimes this is a simple form of interactions that occur as a function of conditions, right? If you have multiple conditions or cross-classified conditions. Sometimes it is interactions of the form of two continuous types of independent variables, and sometimes it's one continuous and one categorical type of variable. So for example, you might place people, the example that I like to use is we might be looking at the amount that a person drinks, and we might say that their impulsivity predicts the amount that they drink, but that impulsivity, the relationship between impulsivity and drinking varies as a function of the amount of avoidant coping that a person engages in. And so in this instance, we will look at people with high avoidant coping and see what the relationship between impulsivity and drinking is, and people with low avoidant coping and see what the relationship between impulsivity and drinking is. That is a continuous by continuous conditional relationship. We might also say that the relationship between impulsivity and drinking is different for men and women. That's a continuous by categorical interaction, and we'll examine those as well. Those wind up coming up. We start doing interactions after the midterm. All right. Let's talk about my approach to kind of teaching stats. On the one hand, we have the mathematics of it, and we will be dealing some with the mathematics of it, but mostly that mathematics of it will be limited to basic linear algebra. I will ask you to write out equations, linear algebra equations, and understand what's going on, because I think it helps when it comes to plotting your slopes through your clouds of data and understanding what residuals are and understanding how we come up with a variance that's accounted for and so on and so forth. However, this class is more based on the application of multiple linear regression. And so the way that I try to break this class up is by talking a little bit about the theoretical approach using these lectures. Then when you come to class, it will very much be application based. And so we will be digging in to the data in every single class, with the exception of the first class. And we will be looking at data every single time. The data will be online for you, and I will expect you to come to class ready to go. Finally, we have the data analytics of it all. The book points this out, and I really like this statement. Behavioral scientists rely very heavily on the fruits of the labors of theoretical statisticians. My goal with this class is not to have you hand jamming a bunch of matrix algebra or working out complex proofs to understand the underlying mathematics. I had to do that as a graduate student, and I'll be honest, I don't feel that it made me any better of a scientist. What I want you to be able to do is to be able to analyze the data that comes from your studies be able to diagnose problems and make sure that you're analyzing it correctly, and make sure that the problems that you're examining or diagnosing, I'm sorry, not examining, the problems that you're diagnosing within your analytic approach are things that you can correct or things that you can manage, or at the very least, understanding the limitations with those things. And that brings me to this last piece, which is specification and error. As a data analytic tool, multiple regression has the possibility that it provides for taking into account or controlling for statistically variables that may get in the way of inferences about the influence of other variables on our dependent variable. These operations within the context of linear regression allow us to do statistically what we often can't do in real life, which is to separate the influences of variables that often or even usually occur together. However, this means that we also have an increased probability of falling victim to specification errors. And as we move through the course, we're going to talk more and more about what specification errors are. But suffice it to say, you have to have a good theory, and you have to know your theory in order to make sure that what you're doing does not fall victim to specification error. The two main types of specification errors that we're going to have to look for are assuming that our relationships are linear when they may actually not be linear, and assuming that the relationships that we have don't function as aren't moderate or aren't associated with each other because of some other variable, or don't function or because of the function of other independent variables. So, more technically, specification errors include conclusions that some relationship that we seem to have uncovered in our sample data generalizes to the population, when our statistical analyses are biased by distributional or non-independence problems in the data. So we're going to focus a bit on understanding the assumptions that come within or that are made for multiple linear regression, and what happens when those assumptions are violated, and how those violations can lead to specification error. Computation. All right, let's talk really briefly about this. Everybody should come to class ready to do data analysis. You can bring your own computer if you wish. Class is in a computer lab, and we will be analyzing data in every single class. We're going to be using computers. I don't believe in doing these things by hand, not at this level, not at the graduate level. So I'll be perfectly honest with everybody, not a fan of SPSS, but since that's what you guys get for free, that's what we're going to use within this course. When it comes to reporting, I follow a general rule, which is you should use basic APA standards, which is 2 decimal points. Especially for slopes, F values, whatever, it should be decimal points. When possible, you should use exact decimal points or round at that third decimal. The only real exception to this is p-values. I like to use 3 decimal points for p-values. This is my own personal preference. You guys will learn this as we get going, but yeah. And that is it. We'll talk a little bit more about these things in class on Thursday. If you have any questions, comments, or concerns, you should shoot me an email. Otherwise, I will see you all on Thursday.